Hey there, team. All right, ready for the second video on equilibrium here. So we covered just generic equilibrium last time, where you got two opposing processes occurring at the same rate. If it's dynamic, they're in constant random motion. But we're going to look specifically at chemical equilibrium today. So what we're interested in is chemists, all right? So same idea. We got two opposing processes occurring at the same rate. In this case, for a chemical reaction, we've got a reaction that's reversible, okay? And so it's got a forward reaction and a reverse reaction. And I apologize for the green fingernails. The lucky leprechaun got me every St. Patrick's Day. Sometimes it gets my hair, but it takes forever to get this stuff off. So I'll have to find some chemicals to remove this green off of my fingernails. But for now, you're stuck with it, right? But for chemical equilibrium, we've got the reversible reaction occurring at the same rate in both directions. And so we're going to do this with just a generic type of reaction, right? So no specific reactants or products. Let's just say we got A and B reacting to form some products. Let's call them C and D, all right? So something simple. So we got species A plus species B forming species C plus species D. Pretty simple generic reaction, right? Now, of course, we need to balance that chemical reaction. So let's just use smaller case letters for stoichiometric coefficients. So let's call that A, little b, little c, and little d. So we got a balanced chemical equation there. We'll talk about the impact of phases in a second, whether it's a solid or a liquid or aqueous or something like that. But what happens is when A and B collide, obviously with enough collision energy to overcome the activation energy, proper molecular orientation, remember collision theory from kinetics, right? So boom, they collide, they're forming these products. But these products in a lot of reactions, many reactions, could also then, as those are growing, these concentrations are going down, these concentrations are going up, and as these increase, you could start getting the reverse process happening, okay? And when those two processes occur at the same rate, now we're at equilibrium, right? So we can also get that reverse reaction. So whenever you see those double arrows, those reversible arrows, you know you've got an equilibrium problem. That's your big sign. Oh, I got an equilibrium problem because I got the reversible arrows. But the beautiful thing about this is just like if we have financial equilibrium, right? The amount of money you're making and spending is the same. Your bank account would be the same. If your calories in equal your calories out, then your body weight stays the same. Same thing's true with a chemical reaction. If the forward and reverse rates are at the same value, then the concentrations of all species in that reaction stay constant. That's hugely important for us, all right? We're going to use that in many, many different aspects. And what's beautiful about this was studied, and the law of mass action was discovered from this. All right, so let's look at what this law of mass action is. What they found is if you take the concentration of your products, multiply those together, and raise those to the power of their stoichiometric coefficient. For example, let's take the concentration of species C. Usually it's in molarity, doesn't have to be, but it's commonly in molarity. That's what the brackets mean, the molarity of. And raise that to the power of its stoichiometric coefficient. So we'll put the little c up there. Let's multiply that by any other products we have. So in this case, we've got D. So let's take the molarity or concentration of D and raise it to the power of its stoichiometric coefficient. If you divide that by the reactants in the same way, so let's divide that by reactant A raised to the power of its stoichiometric coefficient times reactant B raised to the power of its stoichiometric coefficient. What they found is that will always equal some constant. And they called that constant capital K. That capital K is called the, surprise, equilibrium constant. All right, so let's write that down. So this is your equilibrium constant. And what's nice about that is you can find those in the back of your textbook or any equilibrium table that you can find somewhere, all right? And you can look them up for specific types of reactions. And we're going to look in the next video at different types of reactions we can apply this to. This entire thing is called the equilibrium expression, right? So taking the equilibrium constant and equating it to the products multiplied by each other, raised to the power of their stoichiometric coefficients, divided by the reactants, raised to their stoichiometric coefficients. That's called the equilibrium expression. This is hugely important. So that's the equilibrium expression. So write that down. That now gives us a mathematical equation where we can calculate stuff. So if I can look this equilibrium constant value up in a table somewhere, and I know the concentration of my reactants and maybe one of my products, I can solve for the missing one. So I've just got these 5 variables here. Depending, some equations have 1 product or 2 products or 3 or 1 reactant or 2 reactants. Doesn't matter. But it sets up a unique mathematical equation for every reversible reaction if it's at equilibrium. And we can now use that mathematically to predict the products of things at equilibrium, or what we'll need to get a certain concentration, or if we know all of these, we can calculate K. It's a beautiful mathematical concept. All right. Now the phase will make a difference in this. All right, so we've got 2 types of equilibrium based on the phases. We've got homogeneous equilibrium if everything's in the same phase, right? So if everything's in the gas phase or everything's aqueous phase, right? So where you got, solutes dissolved in water and reacting in the water medium. That'd be a homogeneous equilibrium. But a lot probably the majority of what you're going to be doing are heterogeneous equilibria, where we've got multiple phases going on, or states. So you've got, maybe a precipitation reaction where you got a couple aqueous phase solutions mixing to form a precipitate, right? Well, you got aqueous phase and you got solid phase. So that's heterogeneous. Turns out when you're writing an equilibrium expression, this is important to remember, the concentrations of condensed phases like liquids and solids are so much higher than the concentrations of things that are more dispersed out, like something that's in the aqueous phase, where you got these solute particles moving around in the water, or things in the gas phase where it's dispersed out. The concentration changes of gas phase and aqueous phase species are so much dramatically higher than the concentration changes of species in the condensed phase, like liquids and gases, that they're essentially constant. So anything that's a liquid phase or a solid phase, we're going to treat those as constant. All right. And essentially, they're going to get wrapped up in the equilibrium constant. We're going to talk about activity, using activities rather than molarities later. So no worries about that. So we're going to fudge it a little bit. So anything liquid or solid phase, we're just not going to include in the equilibrium expression because it's going to disappear and be involved in the K value itself. So let's do a few specific ones. So I'll erase this board and do a few specific ones and show you how to set up an actual equilibrium expression. Okay, so let's erase this and look at something specific. So let's do something that's all in the aqueous phase, right? Things we'll do a heterogeneous one. Let's start with a heterogeneous one. So let's say we've got some silver and some copper or something like that. So let's say we have some solid copper. And let's drop that in a solution, right? So let's say we put that in a solution of let's do a net ionic equation, right? So we've got some silver ions here. Let's say we have a reversible reaction, and the copper solid becomes copper plus 2. And then the silver becomes a solid. So this is a type of redox reaction, right? And then if this is balanced, you'll end up seeing a 2 here and a 2 there. So if that's balanced properly, this will be the overall balanced net ionic equation for that. So if we want to write an equilibrium expression for this, let's set it up. So we've got our K value. Let's take our products, but remember, we're not going to include anything in the solid or the liquid phase for heterogeneous equilibrium because they're assumed to be constant. So let's take the copper ion here, right? So let's take the molarity of that copper plus 2 ion, raised to the power of its stoichiometric coefficient, which would be 1, so we're not going to include that. And then we don't include the silver because it's in the solid phase, assumed to be constant. We're not going to include the copper here because it's in the solid phase. We're assuming that's constant. But we're going to put in the denominator the silver 1 ion squared. So that would be the equilibrium expression for that. And one thing we can do, we're gonna take these K values, these generic equilibrium constants, and a lot of times we're going to put a little subscript, or you'll see a subscript like a W or an SP or an A or a B on there. Those just designate a specific type of equilibrium. All right. So generically, if everything in the equilibrium expression is in the aqueous phase, we can put that as a KC. right? So we could write that as K sub C. Everything has a concentration is in the aqueous phase. And we're going to find out we could do that also if everything's in the gas phase. So let's do another reaction right below that, and we'll introduce all the different types of chemistry, right? So I could write, let's say we have some hydrogen with some nitrogen, and let's say that's forming some ammonia, and they're all in the gas phase, right? And if we balance that, I think we need a 3 there and a 2 there. So here's another balance equation, and let's say that's in equilibrium as well. Now everything's in the gas phase, so this would be a homogeneous equilibrium. We can write the equilibrium expression for this, and we're going to include everything, all right? Because nothing's in the solid liquid phase. So let's write our K down. And if everything is in the gas phase, you could use brackets and molarities. But if everything's in the gas phase, a lot of times you'll also see pressures used, all right? So we could use the partial pressures of these. So instead of a bracket, sometimes you'll see a pressure symbol, right? So we could take the pressure of ammonia squared, right? Because there's a 2 in front of it. And let's divide that by the reactants. Let's take the pressure of the hydrogen, and there's a 3 in front of that, so I'm going to raise that to the power of 3, right, from the law of mass action. And I'm going to times that by the pressure of the nitrogen raised to the power of 1. So that would be the equilibrium expression for this particular reaction. Now, you can use a generic K symbol, but if everything is a gas and you're using partial pressures, sometimes you'll see them put a little P here for KP, right? So a subtle difference. And in a different video, I'm going to show you how to convert from a KC to a KP, all right? Now, in the next video, we're going to look at all the different types of K values we'll run into in further chapters. I'm just going to introduce them all to you so you're familiar with them. And then we'll relate KP to KC in that one. All right, guys? The journey is beginning.